It's not really thermodynamics related, but that was a lot of fun to do. Anyways, hey everybody, welcome to this week's lab walkthrough. This week we'll be going over specific heat. This is the quality of materials to be able to absorb energy at a rate unique to that material. But before we get into all those details, let's go outside and take a look at this week's pre-lab activity. So in this week's pre-lab, you'll be exploring the specific heat of materials around us. The nice thing about cool weather is it provides you with a hands-on, literally a hands-on opportunity to feel how energy is absorbed differently by different materials. Take, for instance, this building made of brick. You can touch a brick and it will feel different as compared to painted metal. There's also the concrete below your feet. And if you were intrepid enough, you could even try wood or glass. Now, you want to be careful not to touch material that is in contact with a warm environment because you may get the wrong impression. But if something's been sitting outside in this cool weather, our own natural thermometer, the sense of touch, should be very informative to help us see how different substances absorb energy differently. Once you decide on the materials that you're going to test in the outside world, simply make sure your hands are completely warm. You may have to rub them together in order to get them back to your normal body temperature, or keep them in a gloves or pocket for a few minutes until they normalize. Then you place your hand on the object, take a picture, remove it, warm it back up. Go to your other object, place your hand on that. Make sure you place your hand in the same way that you did on the other object, and take a picture. Once you've gotten your photos, all you have to do now is put those onto an image, Google what the specific heat of that material is, try and keep it in the same units as you see in the lab manual just for consistency's sake, and then record what your own sense of touch noticed. What did you notice when you touched it? Which one felt like it got cooler faster? Was actually your hand getting cooler? Well, which one felt cooler faster, and how does that compare to the relative specific heats that you looked up and found on the internet? And that's it. Now, back to the lab.
So prior to today, you've already been introduced to the idea of energy, or in particular, mechanical energy. Mechanical energy being energy of motion, energy that we call kinetic energy, and energy of position. We stored energy in the form of gravitational potential energy, and that would be like holding a ball and releasing it from some given height, depending on what space it has available to move to it. And then you have spring potential energy. This is something that you may not have covered yet in the lecture, but you can at least maybe conceive of it that you have energy stored in a spring that then transfers into the motion of an object, for instance, a projectile ball that we did for one of the previous labs. But now you're going to be looking at ideas of thermal energy, energy that is not expressly mechanical energy in the form of something that has a macroscopic motion or macroscopic potential energy. In particular, we're looking at the internal energy, which has to do with the total mechanical energy for the individual particles that make up a macroscopic substance. For example, consider this container of water, which you can see is visualized with several water molecules in it that has two hydrogens attached to a single oxygen molecule, two whites to a particular red. And if we zoom in, there's different types of energy that's associated with an individual molecule. For example, first we have translational motion, which you can see here is the motion of the object translating through the fluid. The rotational energy, the energy that it takes to rotate around in a circle, and then vibrational energy. This is like the spring action as molecules vibrate depending on their temperature. They have small vibration for cold temperatures, large vibrations for high temperatures, and so these various little bits of energy contribute to an individual molecule, and then collectively you add it all up, you have a total internal energy of the substance. So we talk about something called thermal energy, the energy that's available through thermal means to have an effect on the internal energy of the system. But what's really of interest in this particular lab is the idea of thermal contact between two parts of a system that have maybe different amounts of internal energy. We'll label those A and B, and you think about thermal contact as being when they're in such a situation where energy can flow between one and the other. Now, an example you see here, I say that physical contact is not required. And a simple example of that is you walk outside to get warmed by the sun. You're not necessarily in contact with the sun, here's hoping, but just a simple energy that's traveling to you from the sun. The sunlight, the UV radiation, the infrared radiation all contribute to warming your skin and making you feel fairly good, especially after coming out of, say, my lab, which I like to keep chill. So physical contact is not always required, but in many cases it contributes primarily to what happens when you bring things into thermal contact, which is that you have energy transferring between two objects. And we call that heat, and that's when they're in thermal contact, energy can flow, and eventually they flow until the entire system is in what we refer to as thermal equilibrium. That means that the thermal energy of one object and the second object are now balanced, and energy does not flow as a net transfer between those two. So the thermal energy of the object is how much energy it has. It's going to be related to the temperature of that object, and heat is hereby designated to be energy that moves from one object to another through the course of thermal contact.
The key formula when you're covering specific heat is this one right here. Q equals MC delta T. Some people call it Q MCAT. I don't know why. Maybe that looks like an A. Call it like Q MCAT. Where Q represents the heat, which is the energy exchange between two objects of different temperature. The mass of the object, that is changing temperature. The C represents the actual specific heat, this guy. And delta T is a change in temperature for an object. It's important to note that the specific heat is different for each substance. One thing that is important to get out of the way right off the bat, because we define heat, the flow of energy between two objects, as a change in temperature, it should be noted that temperature is not heat. Heat is not temperature. Again, just like with work, with other concepts that we've developed in this class, temperature and heat specifically have jobs to do. Temperature represents the total internal energy that an object has, and heat, which is the change of energy moving from one object to another.
So now we've taken a look at MC delta T, or the definition of heat, the equation, and we consider a system before we have two objects that are in contact with each other. One, object A, a small object that's a solid, usually in this case is going to be a solid object that you can measure the dimensions of, and you have a fluid of a different substance, aka water in this case. They have initial temperatures that are noticeably different from each other. And then after we place them into contact with each other, thermal contact, energy is going to transfer, and they reach an equilibrium condition where you see the temperature of one is equal to the temperature of the other. That indicates that their thermal energy is in equilibrium. And looking at the total energy of the system, we consider that the energy that's absorbed through heat by the cold objects is going to be equal to the total energy that's lost through heat by the hot objects. We sum those up. In this case, we only have two items, object A and object B, and so the equation looks like this. And once we finish, we have an expression that shows MC delta T for both objects. And at this point, you can solve for an unknown value, whether you don't know the particular mass of something, or you want to know what the final temperature of the system is, or what the initial temperature might have been, assuming no loss to surroundings for anything. In this laboratory, you're going to bring some hot objects into contact with cold water, wait for them to come to equilibrium, measure their temperatures, and then use the information available to calculate and determine the specific heat of the unknown object that you're putting into the water, and use that to confirm what you may have already determined through density means to identify what the substance is and how good your values are in contact with that.
In today's lab activity, what you'll be working with is something called a calorimeter. A calorimeter is basically a cup that is a contained system of objects that are not in thermal equilibrium and will take time to transfer energy amongst them until they've reached thermal equilibrium. You can tell they're in thermal equilibrium when the temperature is at a stable, constant value. All stations will come with a calorimeter styrofoam cup, which is basically a nice barrier between the inside world and the outside world. And you take the lid off, like so. Some stations have the second cup, an internal cup, which is a metal container that you'll use to hold the water. If you do not have a cup at your station, that's fine. Just use your calorimeter cup as your cup containing water. But if you have this cup, you place it inside once you have water in it. And then What you'll be measuring is you'll have cool water in this cup that you will measure at some temperatures, hopefully slightly below room temperature. You'll acquire that water from me at the front desk. Nearby your station, there's a burner that's got water boiling on it. Please be careful around that station. The boiling water will contain in it one of 3 objects that you will place into your water and change the temperature of it. So your first one won't tell you what the material is, but it is a large cylinder and there's a string hanging on to it. You'll use this string to hang it up there. We'll show you in just a moment. Smaller cylinder of a different metal, and then a third metal that is clearly a sphere. Once your objects have been heated up properly in the hot water container, you'll carefully carry them by the string over into your cup. Be sure not to leave them out in the air too long so you don't lose energy to the atmosphere. Also in today's lab, you'll be using the LabQuest 2 instrument, which is a multifunctional mobile device that is able to take various measurements. In today's activity, we'll be using it for a thermometer. So you push the power on the side, make sure it may need to be plugged in if you're not getting good charge. So it'll come up to its home screen. Along with it will be a probe, a temperature probe. You'll take the connector, you'll place it in the front in channel 1. Once it fits in place automatically, it should sense that object and go into automatically. If you're on this screen, you simply click the back button and it'll take you and should automatically be reading the room temperature. In this case is 19.2 Celsius. This probe is very sensitive to temperature. If you put even a slight amount of temperature on there, you'll see that it begins to change. So make sure that you're very careful about what measurements you're making and what potentially could be influencing if they're in contact with this probe. These heat stations are exposed filaments, so you want to be very careful around them. They will heat up higher than boiling point, and obviously you don't want to be touching anything that's very hot. There are a couple ways in order to get your object as hot as you need it to, which is the hot temperature of the water. So you want to set this down into the water gently. Make sure it's fully submerged in the water, but you want to be gentle with it and don't let it fall. It should set comfortably in there without touching the sides or without touching the bottom or the sides. Give it a few minutes to warm up to the full temperature. The entire water should be boiling at full boil again. Once it's at full boil, you can use the thermometer. But if you're not comfortable with that, there will be a glass thermometer nearby that should be set in the water only when it's cold before it's heated up in order to get this temperature. The water will not necessarily get all the way up to 100 Celsius. It is not necessary to wait until it actually reaches 100 degrees Celsius in order for you to consider that a valid data point. Once it's been fairly stable for a good 10 to 15 seconds, it's very close to what the temperature is. So now you're familiar with all the equipment that we'll be using in this experiment. Now let's take a look at how you'll be using them and actually walking through the steps of the experiment. So as you may recall, some stations are going to have only the calorimeter thermal styrofoam cup. Some stations will have both a styrofoam cup and a metal cup. If it has a metal cup, you have to take the mass of the metal into account. So you'll measure the mass of the cup empty, and now I've got water in there, and you'll measure the mass with the cup with the water so that you know what the mass of the water that's in the cup that you've collected. Remember, this should be cooler than room temperature. You should be able to collect it from the front of the classroom while you're waiting for your masses to heat up in the steamer. So once you've got the mass, take it, place it inside your calorimeter cup, try and keep your contact to it as limited as possible, and set your thermometer inside. It should begin to move down to a cooler temperature and normalize with what your internal temperature is of your calorimeter. And once it is heated, you carefully try and have them as close as possible to each other. Gently pull it out of the hop, put it over, and set it quickly into calorimeter. Once it's in there, the water should start absorbing the heat and should capture all the heat and start warming up the environment. You may give this a little bit of turn, be very gentle, even though it is a metal probe. We don't want damage to the metal probe. And then once this normalizes, it should take about 10-20 seconds probably to get there. Maybe half a minute, but wait for it to settle down. Once it stabilizes and it's at a constant temperature for a period of time, then you can go ahead and record that as your final temperature of the system. So once you've got your final temperature, you just take that, put that into your spreadsheet. Remember, we don't want any written stuff submitted on this one. This is the formal lab report, so we're going to go for a professional submission. Now let's take a few moments and take a look at the formal lab report itself. So now we arrive at the main point of the stuff we've done this semester, the formal lab report. Now, please be careful. This is not a comprehensive list of everything your lab report should have. These are the key stuff that stands out different from what you've been doing already with your short lab report. What you want to imagine is your short lab report added with some extra bells and whistles. For one, instead of having the title at the top, the title's on its own cover page. This cover page will have your title, your author information, which is your own name, and any lab assistants that you worked with. You also want to have the abstract on the cover page. So this should actually be a subset of the cover page. If you want to know what an abstract is, think about the back of the book that you would look at to see whether or not you're interested in reading. The difference between the abstract and the back of the book is the abstract tells you what the story's ending is. So in that story, you'll say, I made a measurement. We did it this way using this technique, and it was successful. We were within a percentage error. And that's pretty much it. It's 3 or 4 sentences that does that. That goes on the front page. On the next pages, then you go into your intro, your data results, your analysis, and your discussion as you've done in all your short labs. You want to be a little bit more robust here. You want to dig a little bit deeper. For example, in your intro, this is not just a lab activity that gives you a little bit more experience in the lab. Let's go into your own field of study. There's a scientific motivation behind every experiment that we do in your own field as well. So the question is, what materials in your field, of your field, where you're going to eventually be an expert, was material decided upon because of its thermal properties, its ability to absorb heat or to release heat or to conduct heat. That's your scientific motivation for exploring this. Then you get into the actual theory, the Q equals MC delta T, and the conservation of energy, of internal energy, as you see in the lab manual. Then you get into your experimental procedure. You want to talk about that, maybe a little bit more robust than you've done in the previous, but we don't need to make this a textbook. It just needs to be a little bit more thorough. You get into your data results. Your data results, again, just like before. You present your information in tables. If you think a graph can do the job, add a graph. If you don't think a graph would do the job, don't worry about a graph. It's not necessary if you don't think it is. This is your story to tell about the lab activity that you've conducted. When you get to analysis, you want to go into deeper insight. You want to see, is there more to the story? Did you correctly assess what you've got? Is there an explanation for why your percent error, your percent differences are what they are? What is it that you are learning from this lab other than just simply, I got good percent error? Finally, when you get into your conclusion, your discussion, you want to talk about the success of the lab. You want to talk about the success of your results, whether they were successful or not. And you want to be able to explain what you think was the cause. You talk about that in the analysis, and then in the conclusion, you talk about the lab activity overall. What could have been done differently? What could have done better? What about what you've learned in the process of this gives you greater insight into the motivation behind your experiment? Did you gain insight? Was there something that you now understand better because of your ability to make measurements of the specific heat of substances? Remember that once you've written your formal lab report first draft, you can email that to your lab TA for feedback, for comments and remarks, ways to improve on it. Remember, this is something that we want to kind of be professional about. That's why we're going to college, so that we can become professionals and be skilled at the stuff that we do. For other further guidance, you also can check online on D2L for your formal lab report guidance. At the end of the day, your lab will be a little bit longer by page number, but it shouldn't be it should not be twice as long or longer than what you've been doing for your short labs. 6.5, 7 pages is probably about a ballpark that you want to account for when you include your cover page. Well, that's about it for this week's laboratory walkthrough. Make sure that you take the time to look at everything that's in the lab manual ahead of coming to class. There is good information there that may help clarify these concepts before you arrive in the lecture. Until then, takes a few moments, so now we gotta wait. Doom, ding, doom, doo, 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 doo. You're taking forever to get up and all right, great. Well, that does it for this week's walkthrough laboratory. Well, that does it for this week's walkthrough. Well, that does it for this week. That does it. I think that does it. All right.
See you later, alligator.